Hi guys, welcome to this video. My name is Raymond and I am a statistics tutor for AthenaStudies. And today I wanted to show you a little bit about sampling distributions, what they are, and when and why you should use them. So let's dive right into the theory. And to illustrate what a sampling distribution is and why we should use it, I prepared two practical examples for you. So let's look at the two examples, and I want to illustrate the sampling distribution. I want to show you the difference between the two situations. So let's look at situation one. So suppose we have a population of students at the University of Amsterdam who are following the course RMS. And the population has an average grade of 6.0 with standard deviation 1.2. Now, what is the probability that if I pick one student from that population, that I pick a student with a grade of 8.0 or higher? Okay, so that's the first situation. Now let's look at the second situation. Suppose again we have a population of students at the University of Amsterdam. We still have the mean of 6.0 and we still have the standard deviation of 1.2. But let's now say that I don't pick one student, but I'm going to take a sample of students. So I'm going to pick 10 students from the population of students. What is the probability that the sample has an average of 8.0 or higher? Okay, let's look at the first situation. So what is always a good starting point in these exercises is to draw the correct distribution. That went rather well. So the distribution in this case has a mean of 6.0 because all the observations are still centered around that population mean of 6.0, and it has a distribution. It has the standard deviation, of 1.2. All right. And we want to check what the probability is that I find or I pick a student who has a grade of 8.0 or higher. Well, of course, we know the formula for this one because we need to calculate the z-score. We need to translate this value of x is 8.0 to our standard normal distribution, because then we can use the handy z table. All right, so the formula is x minus this one divided by the standard deviation is 8.0 minus 6.0 divided by the standard deviation, which is still 1.2, and this corresponds to a z value of 1.67, and you can calculate this for yourself as well. So to calculate the probability that if I pick one student, I by accident pick a student who has a grade of 8 or higher, I need to calculate the probability of x is bigger than 8.0, and that is the same as we just calculated as a z value that is higher than 1.67. And recall that we can calculate this in two different ways. We can either calculate 1 minus p, the probability that z is smaller than 1.67, or because of symmetry, you could also do the probability that z is smaller than minus 1.67. Those two should be exactly the same, and in fact they are. And if you look at your z table, then you will find a value of 0.0475, or in more convenient words, I have a 4.75% chance to, by accident, pick a student who has a grade of 8.0 or higher. Okay, so that was the first situation. Let's look at the second situation in which we pick a sample of 10 students. So what I need to do, because we're working with a sample, is I need to draw the sampling distribution. My drawing doesn't get better over the years. Very sorry. I hope you can still recognize the normal distribution in there. But the sampling distribution still is centered around the mean of 6.0. But in this case, the standard deviation is not called the standard deviation anymore, but it's called the standard error. And it is very important that you realize what we are seeing in this sampling distribution, because we picked a sample size of 10. So that means that, for example, in my first sample, I pick the first observation in my sample is someone with a 5.3, second one is someone with a 6.7, third one is someone who has 8.1, for example, really high number. Fourth one, for example, is someone with 3.2, etc., until I have 10 observations within my sample. All the points that lie on this sampling distribution are not single observations, but in fact, all the points in the sampling distribution are outcomes from an independent sample. So from x2 is 10 observations, x3 is a sample with 10 observations. All these data points correspond to an independently taken sample. And realize that all the observations within the sample are still centered around that mean of 6.0 and have a standard deviation of 1.2. So all the observations within the sample still have the same mean, are still centered around the same mean and have the same standard deviation from that mean. But you can already see here that if I take a couple of observations within a sample, it is much more likely that the mean of all the observations within that sample will center more closely around that mean. Because, for example, let's say that if I don't take 10 observations or 10 students within a sample, but I take 1,000,000 students within a sample, my sample will very likely be very, very, very close to the mean, because it's very unlikely that in my sample I will pick only students that have a very high grade. It is much more likely that in my sample, if I take 10 students again, that I pick a student who has a grade of 6.5, someone who has 5.1, so it will center much more closely around the mean. So in general, we can say that for the sample size n, if it goes to infinity, so it gets really, really high, for the limit of n goes to infinity, my sampling mean will be exactly equal to the population mean. So what does this rule say? The bigger the sample size, the more closely it will center around the mean. This is very important. And how much more accurate do we get? The standard error is the standard deviation divided by the square root of the sample size. So you can see in this formula that if my n, the sample size, gets really, really large, I will get something, I will get a sampling distribution. It's so difficult to draw with my mouse, sorry. I will get a sampling distribution that looks something like this. The amount of error will be much, 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 much smaller. So let's look at what this means to the outcome of the probability, because we still have the z, it is still x minus mu, but this time we have to divide it by the standard error, and the standard error, as we saw, is the standard deviation divided by the square root of n. In this case, we have 8.0 minus 6.0 divided by the standard deviation is still 1.1, because remember, all the observations still have the same standard deviation divided by the square root of the sample size, which was 10, and this the outcome of this sum, this formula is 5.27. So once again, I can now calculate the probability that I find the x value which is bigger than 8.0 is in this case the probability that I find a z value that is higher than 5.27, and you can go to the z table because once again we can either calculate this by using the symmetry of the normal distribution or by doing it like this. But you can already see in your Z table that it doesn't go as far as 5.27. I think it goes to somewhere like 3.4. And at 3.4 already you can see that the probabilities get really, really small. So this probability is somewhere around 0%. So as a comparison, remember that for individual observations, you just take the normal standard deviation, and in this particular case we get a probability of 4.75%. And when we are working with samples, remember that the sampling distribution displays the outcome of all the different independent samples that you could take. And then we need to use standard error here, which is the standard deviation divided by the square root of the sample size. And remember that for bigger sample sizes, the bigger the sample size gets, the more closely the sampling distribution will approach the true mean of the population.